In this video, we are going to be looking at two different ways to represent probabilities. One will be an area model, and the other will be a tree diagram. So first, we're going to look at an area model. In previous courses, you've studied probability, which measures the chance that a particular event will occur. Over the next couple lessons, we're going to look at a variety of situations that will require these probability calculations, and you're going to develop new tools. We're going to focus on listing all of the possible outcomes, which is called the sample space. We're going to use this problem to study our area model. It says, can you bend your thumb backwards at the middle joint to make an angle, like the example, or does your thumb remain straight? The ability to bend your thumb is thought to rely on a single gene. What about your tongue? Can you roll your tongue into a U? If so, you probably have the special gene to do that. So we're going to take these two characteristics and make them into a probability model to show the possible outcomes. So I put my first option here on the left, my second option here up top, and then I've listed yes and no, whether or not people can do it. And then to go find the possibilities that people have these different two combinations, I'm just going to multiply the dimensions for this area. So I'm going to take a half times a half and get a fourth. This almost reminds me of the generic rectangle that we use. A half times a half is a fourth here. I'm going to work my way through this, and I can see that each one of these will have a probability of 1/4. Okay, so this area model just gives me a way that I can organize this information. And if I look at this, I notice all of these add up to 1, which makes sense because these 4 possibilities would encompass all the people that either can bend their thumb or not and can roll their tongue or not. So it makes sense that the population would be split here into these quadrants. So if I were to ask you to identify from this diagram the group of people who could bend their thumb back but could not roll their tongue, I would choose the yes from this column and the no from this column, and that would be this 1/4 of the population. This problem is really nice because everything has equal probabilities, and it's pretty straightforward. Not all problems have equal probabilities and are this straightforward. So we're going to adjust this table and make it more of an area model to mimic what the actual probabilities may be. If the outcomes are not equally likely, I can use this idea of a table and use it as an area model. And it uses a large square with an area of 1, and it's subdivided into smaller pieces. Turns out that actually only a fourth of the US population can bend their thumbs back. So to adjust that in my column, instead of it being 50-50 like it was before, I'm looking here at yes is a fourth, and the line is cut at approximately 1/4. So it's kind of drawn to scale. And then the 3/4 is where my no goes. How should the diagram be altered to show that 7/10 of the US population can roll their tongues? Well, that means my yes would be about 7/10, and my no then would be the remaining 3/10 of the population. So my line should be closer to here. And then I'm going to go ahead and actually find those probabilities. So to find the probability of this rectangle here, that is that someone could bend their thumb but could not roll their tongue, I'm going to take a minute and multiply the 1/4 by the 7/10 and get my answer and put it in the rectangle I have highlighted. To find the probability that someone could not bend their thumb but could roll their tongue, I would take 3/4 times the 7/10 and get 21 out of 40. And I can express my probability as a fraction, so it's just fine to leave them as a fraction. These are nice, clean fractions. They're not too large of numerators or denominators, so I'm just going to leave them. Again, I'm going to fill in my area model here, multiplying 3/10 and 1/4 gives me 3/40. If you want, you could do that off to the side. But then make sure you put the probability in the rectangle. And then the last one is 3/10 times 3/4. Multiplying numerators gives me 9. Denominators gives me out of 40. Now, if I check my work, I should be able to add these together and make sure that the probability is out of 1. So I'm going to go ahead and write them all out. So if I add these 4 together, I should get 40 out of 40, and I get 28 plus 12 out of 40. Yep, I get 40 out of 40, or 1, or 100%, which is what my probability is out of, so that makes sense. The square should have an area of 1. What's nice about this diagram is it's really easy to get your answers if you need to find a probability. So this asks, what is the probability that a randomly selected person can roll their tongue but cannot bend their thumb back? I want you to take a minute, answer the question in the video. So we're going to look at one more game before we jump into tree diagrams. We're going to do one more area model. You're going to play this game where you're going to spin. The first letter comes from spinner 1 and the second letter comes from spinner 2. If you can make a 2-letter word, you win. Otherwise, your teacher wins the game. Okay, so the first thing I need to check before I do this area diagram is that these are independent. That is, when I spin spinner 1, does that have any effect on what I'm going to get for spinner 2? The answer is no. There's no correlation between what happens with spinner 1 and what happens with spinner 2. These are entirely independent of each other. So the first thing I'm going to do is I'm going to put spinner 1 on the left-hand side. And then I'm going to go ahead and label, and I have mine drawn, so I'm going to put my I here, and I'm going to label that it's about a half. And then I'm going to fill in the U and the A. If you need to pause the video as we go along to fill in yours, you can do that as well. I'm going to label spinner 2 up at the top. And the T is 1/4. And the F is my bigger chunk here, which is 3/4. Now I tried to do my best to make them match up. If you look here, A is 1/3, so that's a little bit bigger than U for 1/6. So then my next step would be go ahead and fill in this area model. I'm going to go ahead and multiply my two probabilities. A half times a fourth is an eighth, and that would give me the letters I and T making a word. I'm going to multiply a half times 3/4 to get 3/8, and that would give me the letters I and if. I like to write them in the middle, what I'm going to get. It kind of helps me keep track of things. Multiplying a third times a fourth gives me a 12th, and that word would be at. And then multiplying a third times 3/4 would give me 3/12, or I could simplify that to 1/4 if I wanted to. And that would be FA, that is not a word. And then the bottom row, I'm going to multiply again. I'm going to get 1/24, and that's going to be TU. And then I'm going to take 1/6 times 3/4, which is going to be 3/24, or 1/8. And that would be UF, that is not a word. Okay, so I want you to take a minute and I want you to look at this outcome. If you played this game 100 times, who do you think would win? The student who wins if you get a word, or the teacher who wins if you don't make a word? Is this game fair? A major advantage of the area model is that it gives you a really nice way to keep track of the pieces of information. So let's say I wanted to calculate the probability that you win this game. Now remember, you win if it can form a 2-letter English word. So I'm going to go through and circle all the ones that make words, and then we're going to add those probabilities together because those are all the ways that you would win. So I'm going to take an eighth plus 3/8 plus a 12th. And then adding those together, an eighth plus 3/8 is 4/8 plus a 12th, but 4/8 is the same as 6/12. Who knew you'd be getting a fraction lesson today too? So the probability that you win the game is 7/12. It's not a fair game because it's not a 50-50 probability that either person would win. You don't have an equal chance of winning or losing. All right, let's take this same game and let's make it a tree diagram. I'm going to make the first spinner my first set of branches. Now you've seen some tree diagrams in your homework, so we're familiar with how they start. I'm going to label them I, U, and A. Then I'm going to take my second spinner and make that a new set of branches from each branch point here. And I'm going to label T and F, and T and F, and T and F. The problem with this drawn as is it looks like everything has a 1/6 chance because there's 6 different branches here. But I know from my previous diagram that those probabilities are not equal. So when I'm drawing a tree diagram, I absolutely need to make sure that I put my probabilities in there so that I can calculate the probabilities correctly. So let me show you how to do that. So I'm going to go back to my spinner with my probabilities. The probability of getting an I is 1/2. So I'm going to place that along the branch between the branch point and the I. My probability for U is 1/6, and my probability for A is 1/3. I'm going to do the same thing with the T and the F. The probability of a T is 1/4, and the probability of an F is 3/4. That goes between the branch point and the end of the branch. Okay, now in this case, to find the probability of getting an I on the first spinner, which is 1/2, and then the probability of getting a T on the second spinner, which is 1/4, I'm going to go ahead and multiply down the branches. So I'm going to take 1/2 times 1/4, and that's going to give me 1/8. I'm going to put that final probability at the end so I can see the probability of working my way down here. 1/2 times 1/4 is 1/8. To find the probability of getting the word if, it would be 1/2 times 3/4. So I'm going to work my way down that branch and fill in these probabilities. Now I'm kind of showing my work off to the side here, but I would like to point out at the same time it is very clear what my final probability is, and I need to make sure that I keep that. There's a lot of fractions here. I want to make sure that I keep them organized. That's 1/4. Now if I compare the models to the original, all the probabilities are going to be the same. In fact, I want you to pause the video and take a look at what you have from your notes from the previous page. Check that the probability of it is 1/8, the probability of if is 3/8, the probability of UT is 1/24. Check those probabilities. And you'll see that this really doesn't contain any different information, it's just a different way of presenting it. So the question becomes, which is better? How do you know which model to use? What's easier? Take a minute and vote for your favorite method. The answer to these questions ultimately, though, is it depends. It depends on what the problem situation is that you have. For example, if I think about an area diagram, I can put my first event on the left and my second event here on the right, but I couldn't do another event because where would I put it? You know, when I put this and multiplied, it gets filled up pretty quick. If I were to do a tree diagram, my first event would be my first row, my second event would be my second set of branches, and then if I wanted to do another event, I certainly could. It gets messy, but a tree diagram can handle more than three or more events. An area model cannot. Personally, I think an area model is cleaner. It's a little easier. I don't maybe lose branches, but also there's times when a tree diagram is much easier to use. We're going to look at this last problem, and I think it beautifully illustrates that sometimes different models are better than others. This is my favorite character in all of CPM, by the way. This is Rimshot McGee. He has a 70% free throw average. The opposing team is ahead by 1 point, and he's at the foul line in a 1-on-1 situation with seconds left in the game. So I have a bit of basketball in my history. I don't know if you know that. But a 1-on-1 situation means that a player shoots a free throw. Okay, so the player is going to come up and he's going to shoot the free throw. He's either going to make the free throw or he's going to miss the free throw. If he misses the free throw, that the other team gets the rebound or whatever, it's a live ball. He doesn't get another shot. If he makes the free throw, however, you get one more shot. So I want you to take a minute and guess. What do you think is the most likely outcome? Do you think he's going to get 0 points and miss his first shot? Do you think he'll get 1 point? Or do you think he'll get 2 points? Knowing he makes 70% of his free throws, what do you think is most likely? Now that you've made your prediction, let's check. I'm going to use Rimshot's free throw average to help me with my diagram. So I have it all filled out. If he misses it, he does not get another shot, so I don't even need to put that there. But the probability that he makes it is 70%, or 0.70. The probability that he misses it is 0.30, so that just goes here. And then if he makes it, he gets another shot. And then if he misses it, where he has a 70% chance to make it or a 30% chance to miss it. So I'm going to go through and I'm going to multiply these down. I'm going to take 0.7 times 0.7. This would be 2 points. So he has a 49% chance of getting 2 points. If he makes it and then he misses it, that would be 0.7 times 0.3. I think that's like 0.21. That's just getting 1 point. The probability that he misses it is going to be just 30% because there's nothing there. So because he makes 70% of his free throws, he actually has almost 50% chance that he's going to get 2 points here. This is an example where I feel like the tree diagram is beautiful. It works nicely. I don't even have to make a second branch under where he would miss it. The area diagram is a little messier here. So to make my area diagram, I'm going to start with the first shot. Well, he's got a 70% chance that he's going to make it, and a 30% chance he's going to miss it. But then he gets a second shot, and he's got a 70%. So again, I'm going to draw my line here. He's got a 70% chance he makes it. But if he misses the first shot here, he doesn't even get a second shot. It doesn't exist. So my area model would stop there. And then I would multiply to get my probabilities here. This would be 0.49. This would be 0.21. This would just be 0.30. So my probabilities stay the same, but in this case, I think my tree diagram is a little cleaner because it just stops after the second set. Like it just doesn't have this set of branches if he misses it. That's a lot harder to communicate in this area model. We will be exploring these and practicing these models more and more, and you will learn to see when some models fit better than others. But hopefully this gives you a good overview of the different area model and tree diagrams that you can use to model the outcomes of a probability event.